Alright guys, now we're gonna check our bolts if it's going to be filled and shear. So to check that according to standard, this is the equation that we're using. So it's 0.8 VF, and VF is actually 0.62 multiplied by KR multiplied by FUF, and then you have multiplied by which actually area you're going to be using according to what shear plane you're using. Okay, so we'll see that. So let's go to first by step. So KR is actually a factor depends on the lab connection. So and I said before that the lab connection is actually the distance from the first pole to the last pole. So according to our example, we're having a distance here from 70 millimeters. So I will just write. So the distance is actually here. So distance from the first pole till the last pole in the direction of the force is actually equal to 70. So this is 70 millimeters is going to be our our lab connection. So going back, we'll see that okay. So 70 millimeters actually less than 300 millimeters. So it's going to be KR. Our factor is 1, and we move on for FUF. FUF is actually the minimum tensile strength of the poles, and this is, you can actually take it from the table. According to our table here, you go and see which type of bolts we're using. This is FUF. This is from the standard. So you go, okay, we're having, I think, 8.8. Let's check again which type of bolts we're using. All right, yeah, so we're having 8.8/S. All right, snag tight. So we go here. This is snag tight 8.8, so 830 megapascal. This is our FUF, and then we're talking about this part. So which one? So we're basically using this first part to be more conservative, as saying that the thread is including, and this is I'm going to show you what I mean by that. This is what it is. So you have a shear plane. The shear plane is actually this line. All right, so when you have two blades, you have one shear plane. When you have three blades, you have two shear plane. So the shear plane um, equal to the number of plates minus 1. So you have one shear plane here. This is when we say that thread excluded means the area of shanks that we're using. So using NX. So you go here and say, okay, our plane actually, our shear plane located in our shanks area. So I'm going to use this part, NX. So I say NX, for example, for this example, NX is equal to 1. And I go and take the area of the shanks from the table depends about the type of bolt that we're using. For example, M20, you go and say, okay, M20, what is the area of the shanks for M20, and you got it, and you put it here, and this one is going to be 0 according to that. So if you're using this one and say, okay, this is what you usually do because we want to be more conservative about that, and we say, okay, the shear plane is actually located inside the thread area, and this is actually thread included. This means I'm going to use this part, and this one is going to be 0. And to do that, I'm going to say n is equal to 1, this one is 0, and AC, I go to the table, and surely I'll find it much more smaller than the AO. And our example actually like this one. So we have two splice blades and we have one main blade. And so you have two shear planes. And to be more conservative, I'm going to use this part, the left part, assuming that it's threads included, and take the smaller area. So let's go now and apply these things in our all right. So let's say, so this is actually the shear and bolt. So this is the equation, bolts and shear. This is the equation from the standards. So I'm gonna KR is depends about the length, the lab connection. As I said, we have 70 millimeters, and it's basically less than 300 according to standards. If it is less than 300, so I'm gonna take KR equal to 1. So I have KR here is equal to 1. FUF from the table that I've just shown you here, we're using 8.8/S from the question. So our FUF is going to be 830. So I'll add 830 megapascal here. The number of shear planes is the number of plates minus 1. So we have 3 plates, and it's going to be having 2 planes. All right, so I will assume, and this is what I usually do, assuming that threads are included and to be more conservative in the design. So I will use NN and I will use NX equal to 0, because I will assume that all the bars, all our supplies is going to be in the thread area, not the chunks area. So I will go to the table now and see how much AC I will have to put here for M20. This actually is going to be useless, but I'm going to put it anyway. So let's go to the table, go here. All right, so this is actually the table from the standard. So you go the type of bolts that we're using is M20, and go here. We are assuming thread included, so I'll use the smaller value 225, and if I'm using the AO, it's going to be 314, but I will go a smaller value and do the analysis according to that. So I'll take 225. All right, 225 I'll put here, and the area is going, this one is just neglected because I'm not gonna use it, but I'll just put it anyway. So, okay, so now after making our multiplication, you will find that the VF is actually to be 231. This is kilonewton per volt, and we having more than one volt. So, but I'm going to apply the factor first. So apply 0.8 multiplied by how much force we're going to be hold by volt. So I got 185 kilonewton per volt. So now how many bolts I'm having? I'm having 4 bolts. So I apply the number of bolts multiplied by the number of kilonewton per volt I'm having, and I will get that the N star, the maximum N star that can be carried in my bolts is 741. This is our maximum. So the bolts can only handle 741. If you go back to our first analysis, we find that the blades can hold up to 1050. And this is for the main blade. The splash blade is actually going to carry more. But this is actually to failing in tension, we need 1050. But before reaching this point, we're going to have a failing in our shear. So the maximum now, the maximum force is going to be carried by our port is 741. And according to that, we cannot have more than this value. We're going to carry out the analysis for our bearing and tearing, and then we'll go to our welding. All right.